In a previous video, I derived the Coriolis acceleration equation by analysing velocity vectors of a slider moving on a rotating arm. In this video, I will be deriving the same equation. However, I'm going to obtain the equation by analysing the slider's angular momentum. It's not a proof which has been taken from a textbook which has been rigorously tested. It's more an interesting result which I've discovered for those who might be interested in the topic. So what is angular momentum? When any object with mass rotates about an axis, its mass is going to give it inertia. This will cause the object to maintain its angular velocity around the axis of rotation. This is angular momentum. The formula for angular momentum is given by the following. Where L is the angular momentum, I is the moment of inertia of the mass, and omega is the angular velocity. The angular momentum is a vector quantity, and its direction is the same as omega. In this video, as with the last, I'm going to leave the vector hat notation off the equations, just to make the calculations as simple as possible. If we neglect the mass of the arm, the slider becomes a simple rotating mass. In this case, the moment of inertia I will be given by m multiplied by r squared, where m is the slider's mass and r is the radius of rotation. Substituting this value for I gives the following. There is also one other thing we need to know about angular momentum. For the angular momentum of a system to change, a torque must have been applied to the system. This can be expressed using the following equation, where delta L is the change in angular momentum, delta small t is the change in time, and t is the torque. Rearranging the equation slightly, we have the following. We now have all the information we need to analyse the angular momentum of the slider. Let's take another look at our setup. The arm moves with a constant angular velocity, while the slider is moving outward with a constant radial velocity. Initially, when t equals 0, the slider has a position r1. The angular momentum in this position can be calculated as follows. A small time, delta t later, the arm is rotated and the slider has moved out to a new position at r2. The radius of the slider has increased, hence it has a new angular momentum, L2. The slider has experienced a change in angular momentum. This can be calculated by subtracting L2 from L1. In order for the angular momentum to have changed, a torque must have been applied to the system. Torque equals force times radius. The force is equal to the mass of the slider multiplied by the Coriolis acceleration. The radius will be the average radius between points 1 and 2. Combining these, we get the following expression for torque. This leaves us with two expressions for change in angular momentum. The first being, the second can be found by substituting the equation we found for torque. Setting these equations equal to each other, we can solve for the acceleration. The mass on both sides of the equation cancels out. r2 squared minus r1 squared can be factorised as follows. This allows the similar bracketed terms to be cancelled. r2 minus r1 is the distance travelled along the arm, which is also given by the radial velocity multiplied by the delta t. delta t cancels, leaving the Coriolis acceleration equal to 2 by omega by the radial velocity. There we have it. We have once again arrived at the equation for the Coriolis acceleration. Thanks for watching.